The goal of 3-2 is to understand factoring, which will make more sense when we talk about factoring. But we're going to use factoring again, just like we talked about last time. Factoring is another way of solving quadratics. So we are using factoring as a tool to solve quadratics. This whole unit is going to be about ways we solve quadratics. So we'll talk about what that means in a second. First, we just have sort of this reminder of multiplying polynomials. This will make more sense in a second, of course, but just as a reminder, we multiply polynomials by distributing. So when I distribute my x, it gives me x squared plus 5x, and when I distribute -1, I get minus 1x and minus 5, and then I combine like terms here in the middle, and that gives me 4x, and minus 5 and x squared stay the same, and that's my multiplied polynomial. So factoring is the opposite direction of just what we did, just there. So instead of going from two binomials to a quadratic, we're going from a quadratic, well actually both of these are quadratic, I shouldn't say that, but something in standard form, that's better. We're going from standard form into two binomials, so we're going backwards from multiplying binomials. And specifically, what we're doing is, remember from our last unit when we talked about the forms of quadratics, each form had something that was useful about it. Standard form was really useful for the y-intercept. Factored form was really nice for the x-intercepts. Vertex is for the vertex, right? So a way that we can use that to our advantage is to change things that are in standard form into factored form so that we can see what the x-intercepts are. So that is what we do when we factor. We turn it into factored form. So we're going from standard form here to factored form when we factor, which is a great tool to have in your toolbox because factored form is perfect for seeing the x-intercepts. And we will still use the zero product property, so instead of just using formulas for factored form, we're going to talk about why those formulas are the way that they are, and hopefully we'll get so used to it that it's just as easy as using a formula, except for that it makes more sense than a formula. So we're going to turn the page here and we're going to look at our step-by-step for factoring. First of all, factoring again sort of has some qualifiers. We can't, not every standard form polynomial, not every standard form quadratic can be factored. And it seems kind of specific, but there have to be, so you can use this method whenever a is 1 after you factor out any common factors, and there are factors of c that add to b. So that seems ultra specific and kind of confusing, I'm sure, but we will figure that out in a second. So some things, the idea here is that some things just can't be factored, and sometimes the best way to figure that out is trying to factor it, and if you can't, then you can't. That's that. So we have our steps again down the left side, and so the first step says move everything to one side so that it's equal to 0. That might sound familiar from when we did greatest common factor. That's because it's the same thing we want here. We want to be able to use the zero product property, so we first need it to be equal to 0. So to do that, I'm going to add 10 on both sides because that's the one that's like on its own on the other side. Which gives me x squared plus 7x plus 10. Again, I want to emphasize that even though I'm putting 10 underneath 7x, it does not mean I'm combining those things because those are not like terms. We just have to list them separately because we can't combine them. So now we're left with, and you know what, I'm going to write that meter because that's how I feel. There we go. So now we have it equal to 0. We have an a, b, and a c term. Remember that this is, wait a minute, I'm going to change this color. This is a, this is our b term and our c term. I'm gonna still use those three like names to talk about these terms because they're useful and we're familiar with them. Yes, okay, so we have everything moved over to one side, it's equal to 0. Then it says factor out the greatest common factor. So I want you to notice here that only 2 of my terms have x's. We have a constant, so we can't take out an x. The numbers, the coefficients here are 1, 7, and 10, which also have nothing in common. So we actually don't have, our greatest common factor here is 1, which so we won't even need to do that step. Usually when you need to do that step, it's because you have an a term, which we have an a term of 1, so we don't need that. Next, so we're skipping that step. Rather, we can't do that step. So identify your C value and start making a list of factor pairs for it. So, okay, so if you were in class, which is a bummer if you're not, we play a game for this to make it easier. Because to go backwards from standard form to factored form, we have to sort of solve like a number riddle. And that number riddle is we need 2 numbers that multiply to be the C value and add to be the B value. I will say that a zillion times, I'm sure. We need it to multiply to be C and add to be B. So a very easy way that I have found to teach this is to just make a bunch of factor pairs for 10, or your C value. So you need it to, first of all, you need it to multiply, you need 2 numbers that multiply to C, multiply to be C, and add to be B. So we're going to just make a list of numbers that multiply to 10, because you might be surprised, but there is only a limited number of things that multiply to be 10. So we are bound to run into the answer if we're just listing factors of 10. And 10 is actually great because there's not that many pairs of numbers that multiply to 10. We've got 10 and 1, right? 10 times 1 makes 10, and we also have 5 and 2 that make 10. So I want to be clear that I'm not making a factor tree. That's a different thing. I'm just listing pairs of numbers that multiply to 10. So it looks different. Please don't make factor trees because those won't help you. It's a little bit like it, but we're just making like all of our options for the first factoring, I guess. I don't know, listing pairs of numbers that multiply to 10. And that's all. We only have 2 pairs of numbers that multiply to 10. So here's the tricky part. Now we need one of those pairs to add to be 7. So hopefully you've seen, and that's because our B value is 7. And look at that, 5 and 2 make 7. So that is the pair of numbers that we're looking for, 5 and 2, add to be 7, and multiply to 10. So we have like solved that number riddle, that 2 numbers that multiply to be 10 and add to be 7 are 5 and 2. And once you have those numbers, truly that's like the hardest part of factoring, guys, is solving that number riddle, which is why we play a game in class, because it makes it fun and we get our brains in that mode. We compete and we have candy. It's real fun. So at home, I give you permission to buy yourself some candy today if you can solve these number riddles. So 5 and 2 make 7. Those are our 2 numbers, right? We've solved the riddle. 2 and 5 make 7 and multiply to make 10. So our next step in this process is to write this in factored form. So, and you will read that up to the left there. We need 2 parentheses, it's still equal to 0. Remember, this is in factored form. And factored form has x's in each of those parentheses. And then we just use those 2 numbers that we found, and we put them here, positive 5 and positive 2. And that's it. We've changed it to be factored form, like magic. Like I said, the hardest part about this is solving that number riddle, finding 2 numbers that multiply to 10 and add to 7. Multiply to the C value, add to the B value. So now let me tell you something great. Now we have two things multiplied together that equal 0, and so we can use the zero product property that we were using last time to find what two values of x make this true. So those two things are multiplied together to be 0, so we're going to use the zero product property to solve this by setting both of these things equal to 0 and seeing what makes that true. Because remember, to make those two multiplied things equal 0, one of them has to be 0. So we have two possible values of x that will solve this equation. One of them is going to make this 0, and the other one is going to make this 0. So we're finding those two numbers by solving little like mini equations of both of these things set equal to 0. So on this one it gives us -5 when we solve, and this one gives us -2. Notice that this time around, with greatest common factor, one of our answers is always 0. With factoring, that is absolutely not true. One could be 0, but most likely not, right? So those are our two answers, -5 and -2. So you might notice a relationship between those two numbers and the two numbers that we found, right? And that is that they're just opposite sign from what we found. So I am happy if you notice that and are be able to use that to solve things on your homework. I would just encourage you to know why. Yeah, that's all I'm going to say on that. Down here it says, why do our factors need to multiply to the n term and add to the middle term? So why do they have to multiply to c and add to b? So I'm just going to do a little demonstration here. I'm going to use the two binomials that we just had, +5 and x + 2 here. And I'm going to multiply them back together because that's what we're doing here. We're unmultiplying them. We're doing the reverse of this distribution thing we learned to do. So I'm going to distribute, yikes, I totally missed. Distribute, that gives us x squared plus 2x, and then plus 5x, and then plus 10, or 5 times 2. I'm just going to write it like that because I need you to be able to see this next a little bit. All right, so we have this number 5 and this number 2. Right here we have a 5x and a 2x that we end up adding together, and over here we have a 5 and a 2 that get multiplied together. So you might be able to see here that this is us adding, and this is us multiplying. So finding two numbers that multiply to the n term and add to the middle term is just trying to do this in reverse, right? Trying to figure out what makes this true. So adding those two numbers gets us 7x, and multiplying those two numbers gets us 10x, which is what we do to get back where we started. So one thing that I will clarify too is that there is never more than one thing that works. Like, you'll never find two pairs of numbers that multiply to your n term and add to the middle term. There's only ever one. So once you get one, like, you can stop listing pairs. If you already know what it is, you don't have to list all the pairs of numbers that multiply to the n term. Like, you can stop when you have one because there's only ever one, and you're not going to miss an answer. I would just double check to make sure that it does for sure multiply to the n term and add to the middle term. But once you have one, that's the thing. Stick with it. Okay, so we're gonna do a bunch of examples of these because this is I won't do all of the examples that are in the book today on this video because all of them are down below in the notes. So if you need those examples, please just refer to those. But this this factoring thing is all about practicing over and over again, finding those two numbers that multiply to the n term and add to the middle term. So number 1 is x squared plus 6x plus 5. So I want us to first identify the b and the c, the middle and the n term. I need things that multiply to that number and add to that number. So I'm just off to the side, I'm going to list some pairs of numbers that multiply to 5. And guess what? There's only one. 5 and 1 make 5. And good thing for us, 5 and 1 add to be 6, which is what we needed. So, that's our pair of numbers. Easy peasy. Now we just need 2 sets of parentheses, both have x's in them, and then we stick those two numbers, positive 5 and positive 1, into our 2 factors. And then we set both of them equal to 0 to solve. Because now we're using the zero product property, because there's a product and it's equal to 0. So we have -1, x equals -1, and -5, x equals -5. So our two answers are -5 and -1. Okay, I'm gonna start blazing through these. So, okay, on the notes below, I have changed this one because I think I had a typo, probably. So instead of having 2 as a middle term, and probably because it's impossible to factor like it is, hang on. So instead of having 2 as a middle term and 1 as an end term, I just switched those. So this is 2, x, it's 2. That's 2, and this is 1. Now it's possible to factor, so just scribble those out and change it on your notes, because that's, I have now made it possible to complete this problem because the other one was a typo. So, end term is -2 and middle term is -1. So when there are signs, like positive and negative, we need to include those. So when we get like negative numbers involved, this number riddle becomes a little bit more complicated because one of the numbers has to be negative, and so when we add them, we have to incorporate that negative. So we end up actually subtracting. So -2 can be -1 times 2, or -2 times 1. Right, so once we have a negative value, we have like double the number of pairs, because it doesn't matter where the negative is. So you can either list them separately or just find the factor pair and then figure out where the negative needs to be. We want this to add to be -1. So -2 plus 1 makes -1. Notice that this one, and I will do this in this one would end up being, let me think about it, 2 minus 1 makes +1, which is not what we want. We want it to be -1. So this is not the pair that we're looking for, the other one is. So careful with your negatives. The more practice you have with this stuff, the easier it will become, of course, as with everything, but just be careful. So we have -2 and +1. Notice that this becomes the operation in between the two of them. Instead of having a positive, we have a -2. And now we can solve both of these. We just write our mini equation here and solve it to get x equals -1, and solve this one. +2. Again, I'm setting them equal to 0 because of the zero product property. I know that two things multiplied together means that one of them has to be 0. So we're just finding two values of x that make that true. So our answers are +2 and -1. Again, the opposite signs of our pair of numbers that we started with. Just a thought to think about. Okay, now we have 9 and 6. Maybe you can already tell what the pair of numbers will be, but 9 and 1 make 9, 3 and 3 make 9. I think that's all. Yep. And 3 plus 3 makes 6. So 3 and 3 are two factors. We make our parentheses, and then we have an x at the beginning of both, and then we have +3 and a +3. And then this one, you end up with two of the same thing, which is perfectly fine. But it also means that your solutions here will be the same for both. Like, notice that I'm just solving x plus 3 equals 0 twice. I don't actually need to do that because I already know what the answer is. But we have two answers that equal -3. So just a thought about this, if you are thinking back to your parabola and being like, okay, how can it cross at -3 and -3? Like, that doesn't make sense. And the answer to that is that it only crosses it once. If you get the same answer twice when you factor, the parabola looks something like this, where it just barely touches the x-axis. So this is at like -3, right? So the vertex must be on the x-axis if you get the same answer twice. So not necessary information, but just a thought. Like, if you're confused by getting the same answer twice, it just means that the vertex is on the x-axis and it's on -3. So good information to have. There's a bunch more here, and I tried to throw some curveballs in here just so that, like, when you see them on your homework, you're not weirded out. This number 4 is not equal to 0. That's the curveball, so we need to move this 6 over so that it's equal to 0, and then we can do our factoring thing where we have -6. And remember, the coefficient in front of that is 1. So don't get confused by that. We're trying to find two things that multiply to -6 and add to +1. So this again is a negative situation. 6 and 1 make 6. 2 and 3 make 6. I don't think anything else makes 6. But again, this 6 is negative. So I already can kind of see that I need to use 2 and 3 to make 1, but one of them has to be negative. So if I want these two things to add to be 1, I know I have to make the 2 negative, right? Because if I make the 3 negative, it's going to give us -1. Because -2 plus 3 makes +1. So that's the pair of numbers we're going to pick. Gotta write our factors. And then we have -2 and +3. So when we solve that, also another note as I'm solving this is that sometimes MathSpace will be asking you to factor it, and sometimes it will be asking you to solve it. If it's just asking you to factor it, you don't have to do this little solving this mini equation to get x equals. Like, this right here is factored. So once you get there, if it's just asking you to factor it, like, you just need to write that out and that will be the answer. So sometimes it will be asking for solutions, sometimes it will be asking you to factor it. So factoring is less work because you don't have to go all the way to the solutions down here. Sorry, I'm thinking. Think about which ones are the best for us to do here. Okay, we are not going to do, these two are pretty straightforward, so feel free to get them from the notes if you want to do them. They're there for you. This one is also pretty straightforward. You just have to move the 18 first and then solve it. I'm gonna do number 5, and actually number 5 and 8 both have a greatest common factor that we have to pull out. So I want you to notice something about number 5 here. There is not a 1 in front of the x squared, there's a 2, which changes things. We can't factor unless there's a 1 there. It kind of throws a wrench in our factoring thing, and factoring no longer works if there's not a 1 in front of there. But I also want you to notice that 2, 6, and 4 have something in common. and that is 2, right? 2 goes into 2, 2 goes into 6, 2 goes into 4. So one of our steps on the previous page is that we factor out the greatest common factor. And so I just did that, right? I pulled a 2 out front of this, and what I have left is an x squared, because 2 times x squared makes 2x squared, and a 3x, because 2 times 3x makes 6x, and then a 2, because 2 times 2 makes 4. And now I want you to notice something here, that if we were to divide both sides by 2, these would cancel, and 0 divided by 2 is just 0. So we end up with something that's very similar to what we've seen so far. X squared plus 3x plus 2 equals 0. So we can follow our normal procedure now, because we are able to sort of get rid of that 2 in front of the x squared by dividing it on both sides, by first factoring it out and then dividing it on both sides. So sometimes when you see that there's a coefficient on the first term, what you can do is just factor it out and divide it on both sides, because this side is a 0, so dividing by anything doesn't really change it. But it does super change this side so that we can actually factor it, because before we couldn't. So we have an end term of 2, a middle term of 3. So I need numbers that multiply to 2 and add to 3, and conveniently there's only one option for numbers that multiply to 2 and they add to 3. I almost wrote 6. So those are our two numbers. We can factor it now. We have x's in front, and then this is a positive 2 and a positive 1. And so when we solve that, we end up with x equals -1, as you might have predicted if you've been seeing this pattern, and -2. There we go. So that's sort of a wrench that can be thrown at you. I wanted to address it before you see it on MathSpace, that if there's a number in front of the x squared, you can't factor it. You need to either use a different method or, which honestly we haven't learned a lot of methods yet. So really, if you can't do this, if you can't divide it at this point in our education, we can't really do anything, which you won't see anything like that on MathSpace. You'll always be able to sort of factor it out and divide it and then deal with it like this. So here's another thing that you won't see on MathSpace, but I wanted to address it in case that it comes up ever in your life. Notice that this is actually not a quadratic. It's to the third power. So fun fact, the graphs of these look like this. It's like you turned one side of the parabola upside down. It makes like a wiggly line like that. And if you modify it, it starts looking sort of like a, I don't know what to call that, something. And the reason I show you this is because notice that when this graph has the possibility of crossing the x-axis 3 times, which means that instead of getting 2 answers, we could get 3. Depending on what this graph looks like, which I'm not sure because I didn't graph it, but it could give us 3 options, 3 answers. But the process here is actually quite similar. Notice that there's something in common with all 3 of these terms, and that is an x, right? One of them has an x to the third power, one has an x squared, and one has an x. So there's an x in all of them, which means that we can factor that out. Like, this is another greatest common factor thing that we did up here. Except for this time it's an x. So if we pull an x out of each of these terms, you get an x squared, and a 9x, and a 14. And before, we were allowed to divide on both sides. What happens if you divide by x on this problem, though? If you can't, okay, here's the thing. Never divide by x on both sides, because if you do, you lose an answer. You lose a possible solution when you do that, because you're like making an x disappear, and we don't want to do that. Numbers can disappear all they want. X's are a problem if they disappear because we lose an answer. So we can't divide both sides by x, but we can now factor this thing in here. Like that's something that we are used to seeing. So we have an end term of 14, a middle term of 9. So we are looking for pairs of numbers that multiply to 14 and add to 9. And look at that, 7 and 2 add to be 9. So those are our factors here. So the x we leave alone for now. Oops. X we leave alone, but we have just factored this into x plus 7 and x plus 2, and it's still equal to 0. So now, notice something crazy here, that we have 3 things multiplied to make 0. We have an x plus 7, and an x plus 2. And we can actually, the cool thing about the zero product property is it extends to however many things you multiply together and it equals to 0. You can still use it. Even if there's 3 things, those 3 things follow the same rule. We end up setting all 3 things equal to 0. And that's how we get our solution. So we end up with x equals 0 for that first one because x is by itself and it's like already sort of solved. X plus 7 equals 0 gives us the answer of x equals negative 7. I didn't do that middle step. Hopefully you can make that jump. And then x plus 2 equals 0 gives us a solution of x equals negative 2. So we have a graph here that crosses the x-axis 3 times instead of twice because it's not a quadratic. I promise you won't see this on MathSpace, but I just wanted to address it because the tools we are learning work for more than just quadratics. So it's pretty cool. Okay, one last thing to do before I call it quits on this. I'm sorry that the lessons so far in this unit have been kind of long. I just want to make sure that we're understanding this because it's like, this is like the meat of your Math 2 curriculum is solving quadratics. Like this is the stuff that will come back to haunt you on the ACT and such things. So, so I want to make sure it's clear. So we have one more thing here. This is like a different method. So we've learned so far, we've learned taking the square root, we've learned greatest common factor, we've learned factoring, and now we have difference of squares. So this is one where it's like super particular when you can use this, and you can only use it in these particular situations. But it is very useful when it does come up. Difference of squares is what it sounds like. You can only use this when you have a difference, which means subtraction, particularly and only subtraction. And both of the things are squares. And what we mean by squares is like things that you can square root nicely, or things that you can write as something squared. So 9 is 3 squared, and 4x squared is like, actually I'll do this first. So the first sort of step of this, and you have steps over here, is that you write these things as something squared. So like parentheses, okay, work for me. Parentheses squared, and a minus in between. So notice we have a difference, subtraction, of squares, 2 things that can be written as something squared, right? So 9 can be 3 squared, and 4x squared is the same thing as parentheses 2 and x squared, like 2x times 2x makes 4x squared. Yep, okay, so we've written them both as something squared, and it's still equal to 0. And this one we could go into why, but I simply do not have the time, and because this only works in such very particular cases, I don't go super into it. But I just want you to follow this pattern. So what happens is after you've written both things as squares, as a difference of squares, you make 2 parentheses here, and we're going to use that orange 2x and the pink 3 we're going to have 2x is what goes first in both, and 3 is what goes in last in both. So both of these parentheses are going to have 2x and 3. And then the other weird thing is that, oops, that's not what I wanted. You end up with one of them being adding and one of them being subtracting. And that's just, like I said, we could talk about why that works and why it makes sense, but there's just not time, and because it only works in small situations, I don't go into it. But essentially, you can just follow this pattern where you write the two things as squares, and then you use the what's inside that parentheses in both factors, and then one of them's adding and one's subtracting. So it's like a plus b and a minus b. So it has sort of a formula, I guess, here. This only works, it also only works, there can't be a middle term either for this to work. So it has to be a difference of two things that can be squared. And then to solve these, you just use the same zero product property. You set both equal to 0. And I'll just show you one of these because, there you go. You end up having to divide by 2 and you get fractions, depending on what your squares are. And I will just tell you this ends up making -3 equals -3 halves. Anyway, that's difference of squares. I don't think that you will use it that often. I don't know if there's a math-based question like this, but just be on the lookout. 4 and 9 are very clearly square rootable numbers, so if you end up looking at something like this and going, oh, okay, you can use this method. The other reason that I don't super go into this is because you can also solve this using the very first method that we talked about. We can solve this using taking the square root, by just taking the square root, by isolating the x squared and square rooting both sides. That also works. So, like I said, it's useful in a very particular situation, and that situation you can also use a different method to solve it. So the only way that you'll be using this is because if it's asking you to factor something that's a difference of squares. So anyway, that's my spiel on that. So again, I will remind you that I have a Zoom meeting every Friday at 11. The link is on my Canvas. Please join if you have questions, and I'd be happy to work on your homework with you. Just remember that you have math-based assignment for every lesson that we do, so be looking at that so that you're updated.